Hi everyone, my name is Mama Hazib Bezamzwari. So today I'm going to introduce our compound. Our compound is hemoglobin, also known as Hb. It's a protein in red blood cells that carries oxygen from the lungs to the rest of the body. It is composed of 4 subunits, each containing an iron atom bound to a heme group. Hemoglobin's ability to bind and release oxygen eventually makes it crucial for maintaining life. It also plays a role in transporting carbon dioxide back to the lung for exhalation.
Now, let me explain about the structure of hemoglobin. The hemoglobin consists of 4 subunits where an iron atom is bound to a heme group. Now, let's have a look at this video. Here in this video, we can see there are 4 subunits in this hemoglobin. Now, let me explain about the structure of hemoglobin. The hemoglobin consists of 4 subunits where an iron atom is bound to a heme group. Now, let's have a look at this video. Here in this video, we can see there are 4 subunits in this hemoglobin. Now, let me explain about the structure of hemoglobin. The hemoglobin consists of 4 subunits where an iron atom is bound to a heme group. Now, let's have a look at this video. Here in this video, we can see there are 4 subunits. This figure over here shows the structure of heme group. The heme group is made up of 5 main atoms, which is carbon, iron, oxygen, nitrogen, and hydrogen. There are also covalent bond and dative bond present in the structure of heme. The dative bond found between the central iron atom and the nitrogen surrounding it is also known as iron porphyrin bond. Let us have a closer look at the atoms present in hemoglobin. Let us start with carbon first. Carbon has a proton number of 6, has 6 neutrons and 4 valence electrons. It belongs to group 14 and period 2. The electronic configuration of carbon is 1s2, 2s2, 2p2. This is the orbital diagram of carbon. Hydrogen has proton number of 1. It has 1 neutron, 1 valence electron, and it belongs to group 1 and period 1. The electronic configuration of hydrogen is 1s1. This is the orbital diagram of hydrogen. Now for oxygen, the proton number of oxygen is 8. Oxygen has 8 neutrons and 6 valence electrons. It belongs to group 16 and period 2. The electronic configuration of oxygen is 1s2, 2s2, 2p4. This is the orbital diagram of oxygen. The proton number of nitrogen is 7. It has 7 neutrons and 5 valence electrons. Nitrogen belongs to group 15 and period 2. The electronic configuration of nitrogen is 1s2, 2s2, and 2p3. This is the orbital diagram of nitrogen. The proton number of sulfur is 16. Sulfur has 16 neutrons, 6 valence electrons. It belongs to group 16 and period 3. The electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. This is the orbital diagram of sulfur. Of iron is 26. It has 30 neutrons and 8 valence electrons. Iron belongs to group 8 and period 4. The electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. This is the orbital diagram of iron. Now let us look why these atoms are positioned in their respective positions. Hydrogen belongs to the s block due to its valence electronic configuration, which is 1s1. Thus, we can say that the s block elements have valence electronic configuration of ns1 for group 1 elements or ns2 for group 2 elements. Carbon, oxygen, nitrogen, and sulfur belong to the s block due to their valence electronic configuration, which is 2s2, 2p2 for carbon, 2s2, 2p4 for oxygen, 2s2, 2p3 for nitrogen, and 3s2, 3p4 for sulfur. Thus, we can conclude that p block elements have valence electronic configuration ranging from ns2 np1 to ns2 np6, as p block elements come from group 13, 14, 15, 16, 17, and 18. Iron belongs to D block due to its valence electronic configuration, which is 4s2, 3d6. We can conclude that D block elements have valence electronic configuration ranging from ns2 n-1 d1 to ns2 n-1 d10, as D block elements come from group 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12.
Now, let's discuss about the patterns of properties of atoms within hemoglobin based on their locations in the periodic table. For the atomic radius, across period 2, the atomic radius decreases. The order of atomic radius from largest to smallest are carbon, then nitrogen, then oxygen. Meanwhile, descending group 16, the atomic radius increases. Sulfur has a more larger atomic radius compared to oxygen. For the ionic radius, across period 2, the ionic radius decreases. Nitrate ion has higher ionic. For the ionization energy, across period 2, the ionization energy increases with exceptions due to the electronic configuration stability. The order of ionization energy from highest to lowest are nitrogen, then oxygen, then carbon. Meanwhile, descending group 16, the ionization energy increases. For electron affinity, which is EA, across period 2, the electron affinity increases with exceptions due to electronic configuration stability. The order of electron affinity from highest to lowest are oxygen, carbon, then nitrogen. Meanwhile, descending group 16, the electron affinity decreases with exceptions due to the electronic configuration stability. Sulfur has a more higher electron affinity compared to oxygen. For electronegativity, across period 2, the electronegativity increases. The order of electronegativity strength from largest to smallest are oxygen, then nitrogen, then carbon. Meanwhile, descending group 16, the electronegativity decreases. Oxygen has more electronegativity compared to sulfur. For the melting and boiling points, across period 2, it depends on the structure and bonding of the molecules. The order of highest melting and boiling points to lowest are carbon, then oxygen, then nitrogen. Meanwhile, descending group 16, it also depends on the structure and bonding of the molecules. Sulfur has more higher melting and boiling points compared to oxygen. Now, let's analyze the chemical bonds that are present in hemoglobin. Firstly, we have dative covalent bond, which is the bond between ferrous ion and nitrogen atoms. We have 4 nitrogen atoms within the porphyrin ring, which forms 4 dative bond with ferrous ion. Nitrogen is the donor atom, while ferrous ion is the acceptor. Each nitrogen had a lone pair of electrons, which donate a pair of d electrons to the vacant d orbitals of ferrous ion. This bond is polar because nitrogen is more electronegative than iron, and it creates a dipole moment. Although each 4 of the ferrous nitrogen bond is polar, the heme group as a whole is non-polar because the 4 dipole bond are tetrahedral and it is symmetrical, so they cancel out each other. Next is the covalent bond. So first we go to the covalent bond between carbon and nitrogen atom. So in each chiral ring, nitrogen is covalently bonded to carbon. The carbon-nitrogen bond has a partial double bond due to the delocalization of electrons within the chiral ring. So this bond has alternating single and double bonds, and it contributes to the aromaticity and stability of the porphyrin ring. Next, for the covalent bond between carbon and hydrogen atom, they first will form methylene, which is a single carbon atom bonded to 2 hydrogen atoms. The carbon atom forms 2 sigma bonds with the 2 hydrogen atoms. This is a single covalent bond where carbon and hydrogen both contributes 1 electron. Same as for methyl, it is also a single covalent bond, and it is where a single carbon atom is bonded to 3 hydrogen atoms, where the carbon atom forms 3 sigma bonds with the 3 hydrogen atoms. Now, let's discuss the chemical bonding influence on hemoglobin properties and structure. For nitrogen and ferrous ion dative covalent bond, it will stabilize the heme group, where 4 dative bonds will form symmetrical and stable quaternary structure of hemoglobin. It will help stabilize the ferrous ion position, because if it is not stabilized, it could be oxidized to ferric ion, which is not functional because it could not bind oxygen efficiently. So ferrous ion stability ensures heme group remains functional for oxygen transport. The dative covalent bond also influences allosteric effects because the dative bond is sensitive to changes in pH and oxygen concentration. It will induce conformational changes which alters the position of ferrous ion within the heme group, and this will allow oxygen to be released. Next, dative covalent bond also facilitate reversible binding of oxygen to the ferrous ion because the ferrous ion will form a weak bond with oxygen molecule, and it will allow oxygen to be released. The dative covalent bond also contributes to oxygen affinity. High oxygen affinity means oxygen binds to hemoglobin tightly, while low oxygen affinity means hemoglobin releases oxygen more readily. Cooperative binding gives the entire hemoglobin structure greater oxygen affinity. After an oxygen molecule binds to one of the heme groups of any subunit, other subunits will undergo conformation changes which expose their own heme groups. This ensures efficient oxygen loading and unloading. Next, we go to the carbon-hydrogen covalent bonds. It will influence the stability of heme group because it stabilizes the tertiary and quaternary structure of hemoglobin, helps stabilize the binding of oxygen molecule to heme group, and also protects the heme group from oxidation. The covalent bonds also influence the function of heme group because it influences proper alignment of heme group to globin protein, and covalent bonds also influence the flexibility of heme group because it allows conformational change of heme group to occur smoothly and also facilitates the cooperative binding of oxygen. Next, for the carbon-nitrogen covalent bonds, it will influence the stability of heme group because it contributes to stability of the porphyrin ring. These bonds will help stabilize the coordination of ferrous ion at the center of the heme group and ensures efficient oxygen binding and release by hemoglobin.
Hi everyone, my name is Muhammad Haziq bin Zamzwari. So today I'm going to talk about the real-world applications and significance of hemoglobin. There are 5 components that are related to our topic today. Firstly is the oxygen transport. Hemoglobin's primary function is to bind to the oxygens in the lungs where oxygen levels are high and then release it in tissues where oxygen levels are low. This process is essential for cellular respiration and energy production in the body. The second one is therapeutic uses. Hemoglobin-based oxygen carriers are being researched as blood substitute to treat conditions such as severe blood loss where traditional blood transfusions are not readily available or suitable. Next is the sport and altitude training where hemoglobin levels can impact athletic performance. Some athletes use altitude training to naturally increase the hemoglobin levels and improve endurance. Furthermore, hemoglobin helps in the transport of carbon dioxide, a waste product of cellular metabolism, from the tissue back to the lung for exhalation. Lastly, hemoglobin helps maintain the body acid-base balance by buffering the blood against changes in the pH. All in all, understanding these roles of hemoglobin highlights its importance in both health and disease management. Moving forward, hemoglobin's properties make it vital in various fields. In the medical sector, it measures oxygen levels, diagnoses anemia, and monitors patients during surgery and critical care, while in the food industry, it enhances the color and flavor of certain foods, particularly meat products, and provides a source of iron in fortified foods. And as hemoglobin-based oxygen carrier, it serves as a blood substitute in scenarios where whole blood is unavailable or impractical, such as in remote areas or emergency.